Hi, thanks for your interest in my talk. I am Yang Bai. Today I'll be presenting the work of the 2D proximity-induced topological superconductivity in Business 1.7 and 21.3 to learn 3, which is about including topological insulator, and a comparison to the topological superconductivity in bismuth cyanide, which has a lot of bulk carriers, will also be discussed. This work is done by several groups in University of Illinois at Urbana-Champaign and is supported by Army Research Office, NSF, and DOE. The motivation of this work is to create a platform to study Mariana physics. Right now, there are two approaches. The first one is to combine a semiconductor which has strong spin orbital coupling and a superconductor as proposed in this paper right here. And the second one is to use proximity effect to introduce superconductivity into a topological insulator as proposed by Foon and Kane in this paper in 2008. In the first approach, an external magnetic field is necessary to open the gap at the crossing point between two spin orbit bands. This provides spin momentum locking. Well, the spin momentum locking comes for free if combine superconductivity with topological insulator. But a conventional topological insulator, such as bismuth cyanide, has bulk carriers. When placed in contact with superconductor, for example, niobium, the bulk carrier will also be proximatized, and topological trivial superconductivity will emerge. So in order to study a pure topological superconductivity, we have to eliminate the bulk carriers. And excuse me. In the next slide, I will show you we are able to tune the carrier density at the Fermi level of bismuth antimony telluride by tuning the composition of bismuth antimony. And without bulk carriers, only top surface is proximatized. So only the 2D channel is superconducting. We use an array of small elements as a donor of superconductivity because by making the spacing sufficiently small, the electrodynamics in topological superconductivity is only controlled by topological surface state carriers, not by superconducting electrons. As I said, in unconventional topological insulators such as bismuth cyanide, there are a lot of bulk carriers. There is RPES done on bismuth cyanide, 10 quintable layer bismuth cyanide on top of niobium substrate. As you can see, the Fermi level crossing the bulk band here, and it has a lot of bulk carriers. We borrowed an idea from this paper. This group of people, they did work tuning the composition of bismuth antimony telluride to tune the Fermi level. And we use the same method in our lab. We successfully tuned the Fermi level of bismuth antimony telluride. Here are three Hall data, the Hall data of three different films. The red one is N-type, and the Fermi level, the red one is P-type, and the Fermi level is slightly below the direct point. And the blue one is N-type, the Fermi level is above the direct point, but below the conduction band. The third one, the green one, is only slightly N-type, and the Fermi level is very close to that direct point. Now you probably want to ask, how do we know from the Hall data that a specific film, the Fermi level is crossing only the surface bands, not any conduction band? In this slide, I will use this RPES from this paper to show how we deduce the Fermi level from the Hall data. For example, for the sample 3642, bismuth 0.7 and 21.3 to learn 3, it has 2D carrier density of 7 times 10 to the 16 per square meter and is N-type. From the carrier density, we can calculate the Fermi vector, which is 6.3 times 10 to the 8 per meter. We use this number to trace back the Fermi level by drawing a line at 616 times base right here, and we're drawing the line. It will cross the surface band, and we're drawing another line to find the Fermi level. As shown in this picture, the Fermi level is below the convection band and is above the direct point. So it's purely 2D density, and it's like an N-type. We can perform this calculation for other films. For example, 3597, we can have a Fermi level right here. It's still N-type, but it's a little bit closer to the direct point, and because the 2D carrier density is fewer. So from this calculation, we want to show this Hall effect 2D concentrations incompatible with rigid band bending at the surface. So it is impossible for even there is band bending, it is still impossible for Fermi level that crosses the convection or valence band to give such low 2D carrier density. So the only carriers present in the nano-Allen array samples are topological. Here is the device geometry. This device is an array of niobium dots on a 60 quintuple layer business 0.7 and 21.3 2 film. So here the green dots are niobium. This is the entire array, and the measured area defined by the two electrodes. So we measured 1 square of the array. The sheet resistance is 1,520, and the carrier density is 7 times 10 to the 16 per square meter. The mobility is 587, and mean free path is about 26 nanometers. The KF ranges in the mid to low 10 to the 8 per meter. Here is an SEM of a small area of the array and the cartoon drawing to give you a more clear picture. The pitch size is 200 nanometers, so the distance between two neighborhood dots from center to center is 200 nanometers, and the spacing is about 30 nanometers. So from one edge to another is about 30 nanometers. The dot diameter is about 170 nanometers. The dot diameter here is about 170 nanometers. If in the bismuth-cyanide case, the carriers are bulk plus topological surface carriers, so the electrodynamics controlled by both of the topological surface carriers and also the topological trivial bulk carriers. But in the bismuth antimony telluride case, the electrodynamics, for example, the vortices, is only controlled by the transporter in the topological surface C, which is the area between Allens. Here is an RT data of the array on bismuth antimony telluride. I want to first point out this 200 something residual resistance is not real. It is caused by the very large measuring current, and the actual resistance is about 1.6 ohms. It will be shown later in the IV and DIDV measurement. The onset TC of niobium is 0.6K is lower than the bulk TC of niobium because the smaller size of niobium dot. The proximity factor starts at 0.9K around here. There's a constant residual resistance below 0.15K. 0.15K to the base temperature of 15 millikelvin of the Delft we used. Another thing I want to point out is the region that gets proximatized is a region between, it is only the surface region between two neighboring outlets. There's no signal from the bulk. Here is a comparison of two RT data, one from array on bismuth-cyanide, the other one of the array from array on bismuth array of bismuth antimony telluride. The other one is the data of array on bismuth-cyanide. It is obvious that the proximity proximity effect in bismuth sonate is stronger than it is in bismuth antimony telluride, and also the and also we want to conclude only the topological surface channel of bismuth antimony telluride is proximatized. Why? Let's take a look at the RPAS work. The RPAS work is done on a bilayer system of the topological insulator on top of superconductor. So it's different from the system we study. We study the implant superconductivity. The RPAS studied the C-axis superconductivity, and they directly probe the top surface. We call it the naked surface here. In 4-quintable layer bismuth sonide on niobium, at low temperature, a gap opened. This is a symmetrized image to make the gap more obvious to see. But in the bismuth antimony telluride niobium system, there is no gap. So the superconductivity from the interface of the bismuth antimony telluride does not penetrate through the bulk into the naked surface of bismuth antimony telluride. That's why we can say only the topological superconductivity channel, topological surface channel is proximatized. Here is the IV results of bismuth array on bismuth sonide and array on bismuth antimony telluride. In bismuth sonide, the critical current is much larger than the bismuth antimony telluride. Here, from a negative 0.4 microamp to positive 0.4 microamp, it's only this small range if pictured in the IV plot of array on bismuth sonide. And also, the carrier density of bismuth sonide is much larger than the bismuth antimony telluride, so there are more carriers, more superconducting electrons in the bismuth sonide case. And the coupling energy is also much larger than the coupling energy in bismuth sonide, in bismuth antimony telluride. The bismuth antimony telluride coupling energy is relatively the same magnitude to the thermal energy at the temperature of 50 millikelvin. So we believe this rounding effect, as we can see here, as temperature increases, is because of the thermal noise. Here is a picture from a paper by Halpern and Abugaonkar of their study of voltage due to the thermal noise in the DC Josephson effect. We can compare these two graphs. The rounding effect, the curves right here looks very similar to this one. If you rotate this to the axis of x equals to y, then you find these two pictures are very similar to each other. And we did a little bit of calculation here. The array of bismuth antimony telluride, the critical current is about 150 nanoamp for the entire array. For one single junction is about 1 nanoamp. So that we can attribute the finite slope here at very low temperature to the thermal noise. I also did differential resistance measurement of the array on bismuth antimony telluride. The AC current is again very small, 48 nanoamp, smaller than the critical current, and the superconductivity proximity effect completely suppressed at 0.9 K, which is indicated by this right curve. This agrees with the RT measurement. If we take a closer look at the lower current range, there's a small excitation show up as bias current increases, and the lowest point of this curve gives you the 1.6 ohms differential resistance data, so it's almost zero. So I want to say the proximity effect inside the bismuth antimony telluride expands through the entire array, and the entire array is superconducting, but because of the thermal noise, we do not have a very nice flat differential resistance, a zero resistance. Here is a summary of the work. A 2D platform only top surface states proximatized to superconductivity is achieved. We demonstrated the proximity-induced topological superconductivity that only occurs in the top surface, top topological surface states when the Ball carriers are absent. Without any Ball carriers, topological superconductivity provides an ideal platform for the emergence of Majorana zero modes in vortex cores. Thanks for listening, and I would appreciate any questions and comments. Just send email to my email address or my advisors. Thank you again.